Hello, everybody. Good morning once again, and welcome to our webinar today. Our topic for today is Wellbore stability analysis for mitigating drilling risks and reducing NPV. And our speaker is Dr. Rami Eid. So before we begin, I would just like to do a brief um, introduction of Accrete Energy Limited. Some of us know Accrete, while some of us don't. So we'll just do a refresher of Accrete Energy Limited and what the company is about. So Accrete Energy is a Nigerian energy company with head office in Lagos and operations also in the UK and in the Middle East. Our primary focus is in the upstream oil and gas sector, where we offer services from field management to production optimization, software development and deployment, which is what we are popularly known for. We also have our digital oil field service, which is fast gaining popularity amongst most of the producing companies in Nigeria and outside of Nigeria. We also have our integrated assets modeling service as well. Our vision is to deliver innovative solutions that empower clients to gain deep operational insights into their assets and optimize their productivity, because we believe that if our clients succeed, then we also succeed as a company. And then our mission is to create a future, to help create a future where the energy sector thrives on sustainable practices and general technological advancements. An overview of our services. Like I said before, we offer consultancy services in our integrated asset modeling, digital oil field deployment, field development studies, wireless and remote field data gathering systems. For our software services, we have our very popular integrated production modeling, that's the IPM suite. We have our process modeling, Unisim Design. We have a hydrocarbon accounting service, which is the Axis software. And we have our digital oil field, DOF suites. We offer training services for IPM related courses, general petroleum engineering courses, and petroleum business courses. We also do oil field and technical services. We offer oil field and technical services. That's the wireline, slick line, directional drilling services, and also manpower outsourcing. So we'll just talk a bit about our speaker for today, Dr. Rami Eid, before we just go into our presentation proper. So Dr. Rami is a senior geologist specialized in exploration and development. He has his MSc in seismic-derived geomechanics, his PhD in reservoir characterization. He started his career with Schlumberger, now known as SLB, as a field geologist. He worked as a wellsite geologist. He has done several well log evaluations, both in the rig site and in the office. He has worked in various petroleum basins or provinces from Egypt to the Mediterranean, also here in Nigeria. He has worked as a structural geologist in the Gulf of Suez. He has worked as prospect generator for offshore Mediterranean shale blocks. He has worked as a regional exploration geologist for evaluating the whole offshore Mediterranean basin as an integrated project between the government and Schlumberger, now known as SLB, for 2 years. Currently, he works as a geomodeler and planning engineer and has joined KUFPEC as a consultant geologist. So I'll just leave the floor for Dr. Rami to take us through the rest of the presentation. Thank you so much. Dr. Rami.
Thanks, Atura, for your nice introduction. I will share my slides now.
Please go ahead, Doc.
Okay, do you see my slides? The presentation mode?
Yes, please, we can see them. Thank
Okay.
you.
Good afternoon, everyone. I am Dr. Rami. I will present this presentation on behalf of me and Dr. Ali Maher. He's with us here in this meeting. This session, we will speak about wellbore stability analysis for mitigating drilling risks and reducing the NPV. NPV, it is the non-productive time in the drilling. So before we start our presentation, I will give you a safety moment. If you are in the tropical areas and you have an humidity in your area, so it is not the heat, it is the humidity. It is more than a cliche. It is a danger signal. So if you are working in highly humid areas, so please try to wear light clothes and loose fitting clothes. Drink a lot of water to stay hydrated and work in a cool area, not in a direct relation to the sun. So, if we wanted to know the importance of geomechanics in mitigating the drilling related problems, so we should know the importance of reservoir geomechanics in exploration, appraisal, development, and even in the abandonment. As you know that the reservoir geomechanics has had many applications in exploration, development, and appraisal. So if you wanted to do a pore pressure prediction, we need to do a reservoir geomechanical study. If you have some faults and fractures in your area, and we wanted to know if you are if your faults are stable or unstable, so we should do a geomechanical study. If you have an unconsolidated reservoirs and you are suffering from sand production, especially in the deltaic areas in Nile Delta or in the Niger Delta, and you wanted to do a sand production prediction, so we should construct a geomechanical model. If you have some compaction related problems due to the production from your field, so we should do our geomechanical study. And even in the abandonment phase, if you have an depleted reservoirs and we want to know what is the maximum injection pressure in order to maintain your reservoir pressure, so we should conduct a reservoir geomechanics. So reservoir geomechanics, this is not related only to wellbore stability problems. It is related to the life cycle of your field, from exploration, appraisal, development, and abandonment. So if you wanted to select your optimum mud weight in the drilling, you wanted to drill an exploration, development well, appraisal well, so geomechanics can help you a lot in order to have an optimum mud weight in your area. And if you wanted to select your well trajectory, for example, you don't know what is the optimum trajectory where you can drill your well. So we have 360-degree pressures in the earth. If you drilled in one direction, maybe you will suffer from drilling related problems. And you want to design your well to be in an optimum direction. So the solution is building your 1D or 3D, your geomechanical model, to know what is the optimum well trajectory to drill your well. And if we are working in highly fractured reservoirs, so fractured reservoirs, I mean, if you have a carbonate reservoirs, or if you have very tight sandstone reservoir, if you have a low porosity, low permeability, tight sandstone reservoir, and your fractures, and you wanted to know where to drill your deviated well in order to have the fractures which accumulate the hydrocarbon volumes. So we should use the geomechanics in order to track what is called the critically stressed fractures. So we do an stress analysis for your fractures in order to know what is the optimum direction where you can drill your well. So if you wanted to do an hydraulic fracking, if you have a carbonate or you have a very tight sandstone reservoirs and you wanted to frack your reservoir, so geomechanics can help you a lot in order to know the direction of your hydraulic fracking jobs. And if you are producing from your reservoir for a certain time and you are suffering from depletion, so you started from the initial reservoir pressure, so the pore pressure is it changing with the production, and your ss3 it is called the minimum horizontal stress is reducing with the production. So we wanted to know if you have a collapse inside our reservoir, if you have a reactivation of your fault system. So geomechanics can help you a lot in order to do this job. Sometimes we need to drill what is called underbalance drilling, and we wanted to do underbalance drilling feasibility study. If you have an heavy oil, gas shale, oil shale, tight sand, coal bed, and coal methane, gas hydrate. So geomechanics can help you a lot to solve all these problems which are related to drilling and the problems which are related to production. Nowadays, we have what is called the fashion for CO2 or carbon capture and storage. And geomechanics is playing a crucial role in this part. So if you have this sandstone reservoir and you produced from this reservoir and you wanted to do a carbon capture, so geomechanics will help you a lot in order to know if this fault will be reactivated after pumping your CO2 inside your reservoir. And what about your top seal? So you will have some fractures in your top seal, and your top seal will leak your CO2 storage or not. So geomechanics can help you a lot to perform these jobs and to make a good job for CO2 storage. Again, as I told you, if you wanted to do an hydraulic fracking inside your reservoir, it depends on the nature of your fault system. So before starting to design the hydraulic frac job, you should know the tectonic regime of your area. And hydraulic fracking, it is preferred to be parallel to the maximum horizontal stress. So if you have a normal faulting regime like this one, and your maximum horizontal stress is parallel to the strike of your fault, so the design of your hydraulic frac should be parallel to the direction of the maximum horizontal stress. So in the normal faulting regime, the maximum horizontal stress is parallel to the strike of the fault. So for hydraulic frac design, it should be parallel to the strike of your fault. And if you have a strike slip fault, so this is the direction of the maximum horizontal stress. So the hydraulic fracking should be parallel to the maximum horizontal stress. If you are dealing with a reverse fault regime, you have a compressional tectonics. So this is the direction of the maximum horizontal stress. Your hydraulic frac should be parallel to this direction. Again, as I told you, if you have a tight sandstone reservoir and you have two types of the fractures inside this sandstone, or even if you have a carbonate, so we should analyze and study the direction of the maximum horizontal stress and the direction of the minimum horizontal stress in order to know what are the critically stressed fractures, as these critically stressed fractures will be kept up during different times inside the reservoir. So geomechanics will help you a lot in order to understand the sweet spots where you can target your critically stressed fractures. And this example from this area, so is the compaction risk. So geomechanics can help you a lot in order to know if your area is suffering from compaction or subsidence. So look here to this image as it represents the land losses from 1932 to 2050. So you will see that most of lands are flushed with the seawater, and this happened due to the compaction and the surface subsidence of your rocks. And if you have many villages or cities in the coastal area of these areas, so the seawater will invade the land as you see here. And look to this guy. So this picture from Mark Zuback from Stanford, and this is very nice picture. And this guy is standing on the top of his house, and his house was flushed or submerged with the seawater due to the compaction effect of the reservoir and the land subsidence in this area, and the seawater invaded the land. So geomechanics has many application inside your field. It depends on your problem. So if you have some problems which are related to drilling, or you have problems which are related to production, or you have some problems which are related to exploration and the seal integrity. So I will go deeply inside the application of reservoir geomechanics in the drilling, and what is the importance of reservoir geomechanics for designing your wells in order to reduce the non-productive time. But before going inside the technical slides, I will give you some statistics about the non-productive time in the drilling, and these statistics were measured worldwide. So the company which did these statistics, they collected the whole non-productive time data from many wells or hundred of the wells, and they found that in most of the non-productive time problems are related to whole problems. So the companies are spending 14.9 uh, billion US dollar for mitigating these problems. And we have stuck by problems, we have waiting problems, downhole tool failure, rig repair, and other problems. So if we look to this stereo unit, we will find that more than 50% of the non-productive time are related to hole problems and drilling problems. So the companies are spending billions of US dollar in order to mitigate these problems. But if the companies did a good geomechanical models, so they will save this money and they will reduce the non-productive time. I will give you another statistics for the non-productive time, which is related to geomechanics. So you will see that we have here stuck pipe 2.9%, keck 1.9%, wellbore instability 2.9%, and lost circulation 2.4. So more than 50% of the non-productive time in the drilling is related to hole problems. So the cure for that is geomechanics. So if we don't use geomechanics in a proper way to drill our wells, so we will have this problem. Maybe we will have an kick or blowout. And these pictures are collected from different places in the world. This one is from Egypt, Timsah field, and we have another Turkmenistan areas, and we have another areas. So, and we know the Macondo, if you remember Macondo, and we have an Algerian. So, if we don't apply a proper geomechanical model for drilling our wells, we will land with a failure in our wells. Maybe we will have an blowout or kick inside our reservoirs. So this is for the reservoir pressure. So we should estimate the pore pressure in a proper way in order to save the non-productive time and save our wells. So why do we need a geomechanics in drilling? So sometimes you have shale and we don't measure the stresses around your borehole in a proper way. So you will have a caving. It means that your pore pressure, it could be higher than your mud weight. And if you have too much caving inside your borehole, so you will have what is called stuck of your drilling pipe. So the stacking, it is one of the geomechanical related problem, and we should know what is the proper workflow and the proper way in order to overcome these problems. So if you are drilling an highly deviated well, so maybe we will have what is called key seed problem. And this key seed problem, if we talk on a cross section of this problem, so you will have the shape of your well bore will be like this shape, and you have an key seed problem, so you will have an stuck of your drilling pipe. So geomechanics will help you a lot in order to overcome stocking of your drilling pipe and drill a safer wells. And if you are drilling a well and you have an hydrostatic pressure, which is 4.5 kpsi, for example, and your formation pressure is 3.8 kpsi, so you have very high hydrostatic pressure. So your drilling string will be pushed to the side, so you will have a stuck of your pipe, and maybe you will have losses, or you will take a complete loss inside your reservoir. So geomechanics will help you a lot in order to overcome these problems. So before geomechanics, we were drilling our wells, and after geomechanics, we are drilling our wells. So what is the difference between drilling your wells before geomechanics? What do I mean by drilling your wells before geomechanics? Before geomechanics, we were estimating pore pressure and the fracture pressure only. So if you don't apply a geomechanical model in your field, you are calculating pore pressure and the fracture pressure, especially in the deltaic deposits like Niger Delta and the Nile Delta. And the drilling engineers are telling you this is the mud weight window. So they are telling you we have a very nice mud weight and you can drill your well. So this is the traditional method for drilling the wells before applying the geomechanical model. But sometimes you are drilling your mud weight by this way. So we have a very big mud weight window, and you are choosing what is the best place where you can adjust your mud weight. So if we reduced our mud weight a little bit, it means that I will drill a safe well. But unfortunately, when you reduce your mud weight a little bit and it become higher than your pore pressure, you will have many well pore stability problems. And the drillers are saying, why do we have well pore stability problems and we are drilling above our pore pressure? And from this time, geomechanics came to tell you, please don't depend on pore pressure only. You have another curve above your mud weight here. This curve is called the breakout pressure or shear failure line. If you drill below the shear failure line, so you will have many well bore stability problems. And from this time, geomechanics came in the drilling, and geomechanics came to calculate the shear failure line in order to have a safer mud window for drilling your wells. Sometimes you are drilling your well by a technology which is called underbalance drilling. So geomechanics can tell you how to drill your wells under balance. And the geomechanics in the drilling will tell you the well bore collapse pressure, or we call it the shear failure pressure. So the well bore collapse pressure or shear failure pressure, if we calculate this pressure using the geomechanical models, so you can drill a safer well and you will narrow the mud window inside your area. So before geomechanics, we don't estimate the well collapse pressure. And after applying the reservoir geomechanics technology, we are calculating the well collapse pressure. We don't calculate the well collapse pressure only. We calculate another curve, and this curve is higher than the fracture pressure. It is called the breakdown pressure. So if we cut the fracture pressure curve, maybe we'll have losses, some losses. But if you cut another curve which is standing here, it is called breakdown pressure, so you will have a severe losses. So building a 1D geomechanical model will help you a lot in order to narrow the mud weight window and in order to drill your wells safely. So sometimes we need to drill under balanced drilling, but it is impossible in shale and salt. So this is your formation pressure. So, and this is your mud weight. But sometimes if you have a carbonate and the consolidated carbonate, a stiff limestone, so we can drill under balance. So before geomechanics, we were calculating pore pressure only and fracture pressure, and we will have very wide safe mud window. And but unfortunately, if we drill the closer to the pore pressure, we will have wellbore deformation. And if we drill the closer to the fracture pressure, we will have fluid flow into fracture. And when geomechanics came in the drilling, it is narrowed the mud weight, and geomechanics told us, please, we have another curve here. This curve is called break our shear failure pressure, and we have another curve here. It is called the breakdown pressure, and we calculated the fracture pressure by the traditional methods. So we narrow the mud window. So if you drilled your well inside this mud window and ECD window, you will have the safer wells. So 1D geomechanical model is very, very important in the drilling in order to mitigate the drilling related problems and reduce the non-productive time. So how could we build this model, and what is the traditional method by which we can build a proper 1D or a 3D geomechanical model? So before answering this question, we need to know what are the stresses which are affecting your well bore. So if you drilled your well here and you have an open hole here, we have five types of the stresses. We have the principal stresses which are coming from the earth due to the plate tectonics, and these principal stresses are called maximum horizontal stress, and another stress is called the minimum horizontal stress, and we have the vertical principal stresses. So these are the three principal stresses which were found inside the earth due to the plate tectonics and due to the type of the fault regime. If you have a compressional fault, if you have normal fault, or if you have strike slip faults. And when you drill your well, so after drilling your well, you will have another three stresses inside your hole. We have a stress which is parallel to the well bore. This stress is called tangential stress, or we can call it hoop stress. And we have axial stress, it is the mud column or the mud weight. And we have the radial stress, which is perpendicular to your well bore. So if you wanted to build your 1D geomechanical model for mitigating the drilling related problems, we should understand the stresses which are affecting your borehole, as these stresses can give you a hole collapse. This stress will give you a caving of your shell. This stress will give you the directions where you can drill your well. So we like to drill our wells in the direction of the minimum horizontal stress. So you should understand and know what is the direction of your stresses in order to mitigate the drilling related problems. So we have maximum horizontal stress and we have minimum horizontal stress, and we have the stress of your mud weight. We call it BW. And according to these stresses, we will have here and a compressional force in your borehole, as you have here maximum horizontal stress and the minimum horizontal stress, and we have another compression force in your borehole from this direction. And by these stresses, we will have two major phenomena inside your FMI, formation micro imager. FMI, it is Schlumberger market name, so we can say image log, okay, or EMRI, according to Halliburton. We have what is called tensile failure or tensile fracture from your image log. And we have what is called the breakout failure inside your image log. So if you have tensile failure inside your FMI logs, this will tell you that you are in the direction of the maximum horizontal stress. And if you have shear failure inside your well bore, it will tell you the direction of the minimum horizontal stress. So we can know and understand the direction of your stresses depending on your image log. If you have image log like FMI, OBMI, if you are drilling with oil-based mud, or EMRI according to Halliburton tools. So these tools will help you a lot in order to know the direction and or the azimuth of your stress. If you don't have FMI logs, if you have a dipole shear sonic, so dipole shear sonic can help you a lot to know the direction and the azimuth of your stresses. So before analyzing your stresses, you should understand if you are working in normal faulting regime, or you are working in strike slip dominated regime, or you are working in compressional force regime. Why? If you are working in normal faulting regime, it means that the SV vertical stress is higher than maximum horizontal stress, and the maximum horizontal stress is higher than minimum horizontal stress. So we are calculating the stress magnitude, not only the azimuth of your stress. We need to know the magnitude of your stresses. So before understanding the magnitude of your stresses, we should know the structure regime of your area. If you are working in a strike slip dominated regime, it means that your maximum horizontal stress is higher than your vertical stress, and the vertical stress is higher than your minimum horizontal stress. If you are working in a thrust faulting regime, so compressional tectonics, it means that your maximum horizontal stress is higher than minimum horizontal stress, and your minimum horizontal stress is higher than your SV. So these principal stresses are very, very important if you wanted to drill a deviated well, or if you wanted to drill in a vertical well. These stresses are affecting your well trajectory. These stresses are affecting your well shape. The stresses are affecting the pressure or the pore pressure, and you should understand them before designing your mud weight or your optimum mud weight. So we have SV vertical stress, maximum horizontal stress, and minimum horizontal stress. But if we wanted to build our geomechanical model, these stresses are not enough to build your model. We should calculate the pore pressure. And the pore pressure is very, very important parameter, especially if you are working in high pressure, high temperature areas, deltaic areas. If you are working in over pressurized shale, like what do you have in the Niger Delta. So pore pressure calculation methods is very, very important. It depends on Eton, or we have many methods for calculating our pore pressure. And we should calculate UCS, rock strength. And we can calculate UCS from triaxial test or from logs. And we should calculate the fracture and fault orientations from logs and from the seismic. So if we calculated our principal stresses, and you have SV, you have SH max, and you have SH min, and you have your pore pressure. So we are very, very close to build our 1D geomechanical model. And as I told you before, the direction of these stresses or the magnitude of these stresses is different from area to another area. It depends on the tectonic regime, if you are working in reverse faulting or strike slip or normal faulting regime. And if you have a dramatic increase of your pore pressure, it means that you are working in highly pressurized area or over pressurized shale. So we should put this in our consideration for building our model. And the direction of the stresses is very important, not only for the drilling, it is very important for finding a discovery. For example, if we looked to this field and we have this fault, so this picture is from Mr. Mark Zuback, and it is very good actually, as if you have this fault and we tried to extract what is called root mean square RMS amplitude map. If you have an deltaic deposit, so RMS maps are working very well. And when we drilled a wells here in the highest structure, so this is the high structure area, we found that there is no amplitude in the high structure, and these wells are dry. It means what? It means that these stresses, when we studied or analyzed the direction of the maximum horizontal stresses, we found that these stresses are perpendicular to the fault, and this fault is normal fault. And we know that from the normal faulting regime, the maximum horizontal stress should parallel to the strike of the fault. But here, the maximum horizontal stress is perpendicular to the fault. It means that nowadays we have stress rotation. This fault is very old fault. But when we drill our wells, we are measuring the present day stresses in our areas. We don't measure the value stresses. And when we had a stress rotation here, this maximum horizontal stress made and many fracks in the top seal above your reservoir, and your gas is leak. So you have gas leakage here. So understanding the orientation of your stresses will help you a lot to answer the questions why we have here dim amplitude and we don't have any amplitude here, and we have another amplitude signatures in the another areas. And for your info, stresses are not constant in your field. If you have three fields here, Y and X and Z field, these stresses are rotating inside the field. So if you have one well here and you have FMI and we measured the azimuth of maximum horizontal stress, please don't say the maximum horizontal stress is the same here in the other field. No, as the stresses are rotating from area to another area. Okay, so we should calculate these stresses in our area in order to drill and save wells. Sometimes if you have faults, so these are on a faulty plane, we measure the stresses around the faulty plane in order to know what is called leakage potential of your faults. And this is very important in the CO2 carbon capture storage to know the gas leakage potential of your faults. Where are the leak points along your faulty plane, as you can have a leakage of your CO2 or a leakage of your gas if you are injecting a fluid inside your reservoir. So, if we wanted to build a 1D geomechanical model or a 3D geomechanical model in your field to reduce the non-productive time, we should analyze or study the stresses in your field. After studying the stresses in your field, there is a workflow for building the model. So this is a 10 steps workflow. We should have a data audit. And so we should QC the data. We should collect the whole data inside your field. If we have drilling reports, mud logs, if we have geological reports, FMI, wireline logs, the whole available data in the field are very, very important if we want to build the model. And we should calculate, or we should take notes about the drilling hazard. The drilling hazards are very, very important in the model. If you have an kick, if you have losses, if you have connection gases, if you have tight spots, the whole drilling related problem should be collected. Okay, and we should build the mechanical stratigraphy. Where is our shale? Where is our sand? Where is our limestone? As the pore pressure prediction is inside your shale, not inside your sand. So we should know where is the shaly intervals and where are the non-shaly intervals. After that, we will calculate the overburden stress, SV, vertical stress, using your logs or using your seismic data. And after that, we will calculate our pore pressure. And calculating your pore pressure, we predict the pore pressure inside the shaly interval, and we take the actual reservoir measurement inside your reservoir. And we will calculate our rock strength, our elastic properties, UCS, and Young's modulus, Poisson ratio, horizontal stress direction, the magnitude of the stresses, and the minimum horizontal stress. We can calculate it from the mini frac job or we can calculate the magnitude of minimum horizontal stress from extended leak of test exercise and the maximum horizontal stress. And finally, we will have our failure analysis of our well bore, and we will have the suitable mud weight or mud window where we can drill our wells. So the input data for our model is compressional sonic, shear sonic, bulk density. We will calculate the elastic properties, Young's modulus Poisson ratio, overburden stress, pore pressure, and we will know that the tectonic regime of our areas in order to calculate the magnitude of minimum horizontal stress and the magnitude of the maximum horizontal stress. So we know the accident of the deep water horizon, or this accident is called Macondo, okay? And deep water horizon, it is one of the famous accidents, and this accident is related to a little bit the poor pressure protection. So the company didn't protect a pore pressure in a proper way, or they had a surprise in the pore pressure. So I will give you a brief about what happened in this accident. So the company calculated the pore pressure by this way. So this is the actual measurement, and they calculated the fracture pressure. So this is the traditional method without using geomechanics. You are calculating pore pressure, and we are calculating the fracture pressure. And they were drilling their wells using a high mud weight. Okay, so this mud weight, I think they were drilling it by 14.3. So when they drilled their well by 14.3, they cut the frag pressure. So they took an losses inside the reservoir, and after that they decreased the mud weight from 14.3 a little bit to 14.17, and they drilled this section safely. But they have a reduction in the pore pressure inside the reservoir. They had a reduction in the frac. And after that, they squeezed the cement in order to make an casing. And the cement is the cement weight is very high. It is exceeds 16 ppg. So if you fract your rock by 14.1 and you are pumping cement to case this area by 16 ppg, it means that you are fracking your rock more and more. So the cement quality behind the casing was not good. And after they pushed the cement inside the reservoir section, cement quality here was very bad. When they came out from the hole, so the hole came against them, and they have gain, and after that they had a kick. So here we have a geomechanical related problem. It is called the Macondo accident. So they didn't estimate the pore pressure, or so here we have a reservoir pressure. We don't calculate the pore pressure inside the reservoir, but they had a surprise that the reservoir pressure is very low. Okay. And for pore pressure prediction, so I told you before, we should have this workflow to reach to our final geomechanical model for reducing non-productive time. So we should calculate overburden stress. We should calculate our pore pressure. So I will speak about the pore pressure a little bit. So for pore pressure prediction, we estimate pore pressure pre-drilling. So if we don't have any wells inside our area, we can calculate our pore pressure using seismic velocity, offset sonic, offset resistivity, offset density, MDT data. And while drilling, we can calculate the pore pressure using the D exponent, so from the drilling parameters. And we have BBFG software. We can calculate it while drilling, and we can calibrate the pre-drilling calculated pore pressure. And post drilling, after drilling, we will have an actual measurement of your electrical logs. We will have the sonic log, shear sonic, compressional sonic. We will have density log, so we can calibrate our model after drilling. So for bore pressure, we calculate it pre-drilling and while drilling and post drilling. So calculating pore pressure, it depends on a basic equation. Basic equation, it says SV, S, it is vertical stress. So SV, it is your vertical stress So S, this is S, so it is vertical stress. Could you hear me?
Yes, can hear you.
Yeah, so it is called SV. It is vertical stress. It is equals pore pressure plus sigma effective stress. So this is the basic equation for calculating your pore pressure. So if you want to calculate the pore pressure, so pore pressure is equal SV minus sigma effective stress. So we should calculate vertical stress before calculating your pore pressure. Vertical stress, it depends on a basic equation which is called rho gh, density multiplied by specific gravity multiplied by h, the depth of your rock. And sigma effective, this is we can calculate effective stress depending on many equations, but in the deltaic deposits like Niger Delta deposits, sigma effective can calculate it using what is called the Eaton method. Eaton is one of the famous equations for calculating SV. So what do we mean by this equation? This equation, it means that if you have a rock like this example, and you have here, this is the grain of your rock, and in between your rock we have a fluid. So this fluid, it has pore pressure. So pore pressure, it is the pressure of the fluid inside your rock. And above your rock we have vertical stress. It is the sediment load, the stress of the sediment above your rock. So if the FCV is equal, for example, 5K psi, and your pore pressure is equal 2K psi. So the effective stress above your rock, not 5K. The effective stress above your rock is 3K psi. Okay. So in order to calculate your pore pressure, we don't know the pore pressure. So in order to calculate it, we should calculate our SCV, vertical stress, and we should calculate our effective stress, sigma effective, in order to know the pore pressure of your reservoir. So we use this equation pre-drilling and while drilling and post-drilling. And the Eaton method for calculating the pore pressure, it depends on what is called normal compaction trend. So if you have a sonic log, and for example, by using this sonic log, we can, or by using the seismic interval velocity, we can calculate our normal compaction trend depends on our theta. And after that, we can calculate our pore pressure, and we can estimate our mud weight. And if we talk some connection gases here in this point while drilling, so we should change the gradient or the slope of your normal compaction trend in order to match what happened in your well. So your bore pressure will be shifted. So the drilling related problems are very, very important in order to calibrate your bore pressure. This is another example. If we draw our normal compaction trend, and while drilling, we had another point, is it means that we should shift or change the slope of our normal compaction trend to update your pore pressure. So we are updating our pore pressure while drilling in order to know what is the optimum parameter by which we can calculate our pore pressure. So we had another indications, or we have some indication for the change of the pore pressure around your reservoir, like the seismic velocity, interval velocity, or root mean square velocity. For example, if you have a fault here and here you have an velocity values, these values is completely different than these values. It means that you have a change in your pore pressure inside your area. So again, for building your 1D geomechanical model, we should calculate overburden stress and pore pressure and elastic properties, dynamic elastic properties. We convert them to static elastic properties. We calculate the rock strength and horizontal stress. For the elastic properties, we can calculate the Young's modulus and Poisson ratio. So if we applied axial stress inside your rock, we will have a change of your rock. We call it axial strain. So Young's modulus, it is stress divided by strain according to what's called Hooke's law. So we should calculate Young's modulus. We should calculate Poisson ratio. It is the lateral strain divided by axial strain. And although we should calculate UCS, unconfined compressive strength. So all these parameters, we are calculating them using a triaxial test, the lab test, and using electrical log. But in order to have a proper values of these parameters, we should have a core data. And we should perform an lab test using this core data, and after that we can calibrate the log measurement using the lab test to have an proper values of this data. Sometimes we don't have an lab test or lab data, so we can depend on the empirical equations for calculating them. So equations for UCS, we had many equations for calculating UCS if we don't have lab data or lab test measured data. I told you before, in order to calculate the azimuth of your stresses, we should have FMI. For example, here, if you look here to this image, we can see the breakout is very, very clear. So the breakout is in the same direction of your minimum horizontal stress, and your maximum horizontal stress is perpendicular to your minimum horizontal stress. So if we had a breakout, we can know the azimuth of your minimum horizontal stress, the azimuth of your maximum horizontal stress. And here we have this line, it is called tensile failure. Okay, so tensile failure or tensile fractures, these fractures are parallel to the maximum horizontal stress. So if you have breakout only, we can know the azimuth of minimum and the maximum. If you have tensile failure only, you can know the azimuth of minimum and the maximum. And finally, we can reach to our 1D mechanical earth model. So this is the type example of your 1D geomechanical model. Here we put our elastic and rock properties, the input data for your model, Young's modulus, Poisson ratio, here and friction angle as well. We can put the pore pressure, vertical stress, maximum horizontal stress, minimum horizontal stress, vertical stress, and we will reach to our final 1D geomechanical model here. So the white area is the area where you can put your optimum mud weight to drill a safe well and reduce the non-productive time. This model has 4 curves. Curve number 1 is your pore pressure curve. Curve number 2 is your breakout curve. Curve number 3, it is your fracture pressure curve. Curve number 4 here, it is the breakdown curve. So if you cut the pore pressure curve, you will have kick and blowout. If you cut it inside the reservoir. So, and if you cut the breakout curve here, you will have some tight spots, you could have some connection gases, you will have drilling related problem. If you have a fracture curve, if you cut the fracture curve by your mud weight, it means that you will have some losses inside your reservoir. And if you cut the breakdown pressure, you will have a severe losses inside your reservoir. And we can take this 1D geomechanical model and we can take exact depths. For example, if this is depth is 2000 meter, and if we took this depth, for example, we can have these plots. These plots, it is the deviation versus your mud weight in specific depths. So this will tell you what is the optimum deviation of your well bore in order to drill your well in the white area. And we plot also not only the deviation, the mud weight versus azimuth. What is the optimum azimuth in 360 degree to drill your well safely in the white area? And we can have these stereo nets for shear failure, where is the optimum location to drill your well, and another stereo net for the breakdown pressure. So we can design a proper well, and we will reduce the NPV, non-productive time, inside our wells by constructing the 1D geomechanical model. But Sometimes if you have a drilling campaign, and you have 10 wells or 14 wells, so I recommend not to do 1D geomechanical model only. You can do a 3D geomechanical model. The importance of the 3D geomechanical model, it comes from this cube. If we construct the 3D geomechanical model, you don't need to build the model. By putting the X and Y of your well, so you will have your model by one click. So 3D geomechanical model, it is very, very good if you have an huge drilling campaign. We don't need to build 1D, 1D, 1D. We should have one 3D geomechanical model, and by using this model, we can put the X and Y of any well inside this model. And so you will have your 1D model from 3D model by one click. But building a 3D geomechanical model, it is not easy. It needs more data, as we want to distribute our geomechanical data in 3D, not in the 1D. So we need some products from seismic inversion. We need some products from petrophysics, from geological model, from reservoir simulation. And after we build the 3D geomechanical model, we will have youngest modulus. But youngest modulus, it is not one value, one log. It is looks like seismic section, as this section was taken from the 3D model. So we can have 3D youngest modulus, for example. And in order to calibrate your 3D model, we will have the 1D, and we put the 1D result above the 3D result. Here, youngest modulus cube from 3D, youngest modulus log, in order to calibrate the 3D model. And for Poisson ratio as well. So the whole geomechanical properties, we will have them in a 3D, not a 1D. Okay, so if you wanted to design any well here, another well here, at any location, you can have by one click the elastic properties of your rock. But we have to calibrate them. So we will have the Poisson ratio from the Poisson ratio cube and put it above the Poisson ratio from the 1D. And we construct our geomechanical grid model. So this is your reservoir interval. We have what is called overburden above your reservoir, side burden, your reservoir under burden. We are trying to simulate the subsurface. Okay, so in the 3D, we are simulating it, and we should map the overburden layers above your reservoir in order to do simulation for it, and under burden. And one of the results of your 3D model, it is the 3D bore pressure cube. So this is bore pressure cube in the 3D, not bore pressure in 1D model. So it will give you a good insight about the 3D distribution of your bore pressure. And finally, we can extract 1D model. This is 1D model from the 3D cube at any location, at any well, to have your well bore stability model and to mitigate the drilling related problem. And we can design our well. So by this way, we can know the orientation of your stresses in a 3D. So we can design a proper well in order to reduce the drilling related problem and reduce the non-productive time in the drilling. This is the references where I took my slide from them, and I would like to thank you for your patience and for your attention to my session. If you have any question, feel free to ask me, please.
Thank you so much, Dr. Rani, for for this presentation. It was very insightful. I believe we've learned a lot. So the floor is open for questions. We just give everyone access to speak. So if you have any questions for Dr. Rami, please go ahead and ask your questions at this point. Okay, Dr. Rami, someone is asking if we can get this slides after the presentation.
Yes, I will send you the slides, Adora, and you can distribute them to the attendees.
All right, thank you so much. Do we have any other questions? Okay, we have a question from Osarugwe. Okay. Please, you can ask your question. You can unmute and ask your question, Mr. or Miss Osarugwe. Thank you. Yeah, I think you can speak now. Please go ahead.
Yeah, good afternoon, doctor. Good afternoon, everyone. Can you hear me?
Yes, I can hear
Yes,
you very
please.
well.
Okay, so it's a very nice presentation, and this is something we face almost every time in the field. But my quick question is there a way we can estimate? I see one of the main parameters for this MEM, mechanical health modeling, is the UCS, which you get from your logs. But sometimes in operation, we have bad data from some sections of our logs. Is there a way you can go around that?
Yes, I told you that we should have some logs or basic logs in order to calculate your geomechanical problem, your geomechanical parameters, like the density log, shear sonic log, and the compressional logs. But if you don't have these logs in order to calculate your UCS or Poisson ratio or Young's modulus, we do correlations using your offset data, and we use these correlations in order to calculate them in the areas where you don't have a data. For example, if you have a bad operation in your area and it was very difficult for you to acquire logs, but if you have seismic interval velocity, we can convert this velocity to density, and density and the sonic using some equations like Gardner equation, and we can mitigate these problems and we can build our model. Is it okay?
Yes, thank you. Thank you very much. And please, I
Okay.
would really appreciate if the recording can be shared with us as well.
Oh, the recording will be shared. Okay.
Okay.
Okay, we also have questions from Mr. Francis. Mr. Francis, please go ahead with your question.
Okay, thank you for the opportunity, cause to be part of this session. And thank you, doctor, for the exposition. I just want to ask. I had have a personal experience drilling through a fault zone at about 11,600 feet now, not meters. And then we were told that it was a ceiling fault. But of course, when we drilled into it, we started having all manner of hole instability problem. The mud weight at the time we drilled into it was about 10.5. So we struggled to come out of hole, and we have not actually drilled to TD at that point. We thought we're having maybe our BHA is bored up or stuff like that. Eventually we came to surface, everything looks good. So we can't really tell why we were having to struggle. But we noticed that over the shakers, we're having a lot of cave-ins. So that gave us a clue that maybe it is the fault that we're actually, battling with. Now, the strategy that was employed, the mud weight was increased to about from 10.5 to about 12 ppg. My question is, would that be the first action when you I wouldn't know if they did any geomechanics modeling, before they arrive at whatever decisions they took. But should that be the first action whenever you drill into such fault zones? That's my question. Thank you.
Okay, so you had a problem. So I don't know if you did a geomechanical model before facing this problem, or you didn't build the model. So if you had an approval geomechanical model, especially for the fault zone, we are estimating the pressure along the fault zone. For example, if the depth of your reservoir is 3K meter, for example, and you face your fault at 2.5K meter, we are estimating the pressure along the fault plane. So there is no relationship between the fault seal analysis by the traditional method and the fault seal analysis using a geomechanical model. Sometimes we do a fault seal analysis using a traditional method like shale gauge ratio calculation, clay smear, and we land that our fault is sealing. But after conducting our geomechanical model, we found that the faults are not sealing, as the stress distribution along the fault plane is not the same. So the answer for your question is that if you constructed a geomechanical model for understanding your fault seal integrity, I think that you will not face this problem. Is it clear, Mr. Francis?
Sorry, I lost you like the last 30 seconds.
Okay, you lost my answer?
Yeah. I think the last, maybe your last sentence or something.
Okay, so I am saying that if you constructed a geomechanical model for understanding your fault seal integrity, you will not face this problem, as there is two methods for calculating the fault seal analysis. There is a traditional method by using shale gauge ratio, clay smear, shale smear. And this method is not sufficient at all. Sometimes you can say our fault is sealing by using a traditional method, but after applying a geomechanical model along your fault, you will find that your fault is leaking. So the answer for your question is that you should do and construct and study for fault seal analysis using geomechanical data in order to overcome any surprises during the drilling.
Okay, that's clear. I'll presume that the client did not do any geomechanical modeling because it turned out to be a guess that the fault is a ceiling fault, and
Yes.
of course we eventually realized that we have all manner of problems. All right, thank you, Doc. I appreciate.
All right, we also have a question from Mr. Kola Bakari. Mr. Kola Bakari, please go ahead.
Good afternoon, all, and thank you, Doctor, for your presentation. I am more of a commercial person, and my questions are going to be commercially based. I actually have two. Now, take, for example, you look at the commercial challenges such as data acquisition costs, computation complexity, model validation, and uncertainty. And then you also think about industry expertise and adoption. I'm wondering how can the value proposition of a geometric model be better communicated to convince companies that it's important to do this? First, question one. And then should, in case they don't even do a geomechanical model, what would you advise them to go about doing, should in case they can't do that? These are my two questions, please. Thank you.
Okay, so from the commercial point of view, you will ask the company one question. How much money do you pay for drilling one well? He will tell you, for example, we will pay 10 million US dollar for drilling this well. you can ask them another question. How much money did you pay for acquiring wireline logs? He will tell you 0.5% of the well budget. So I need you to understand, if you are spending 1% or 2% from the budget of drilling your well for acquiring the data, and if you faced any drilling related problem, you can drill one well and the side track, and sometimes we cannot complete our well at all. So eh, from the commercial point of view, geomechanical study, the cost of the geomechanical study is nil. Okay, and if you compare the result of this study, it will help you a lot to drill a safe wells. Maybe you will spend $1 million for doing a study, for example, and maybe you will spend more than hundred of US dollar hundred of millions of US dollar to mitigate the drilling related problem. Okay, so the role of geomechanics specialist, it looks like the role of the doctor. If you have a pain, so if you don't go to the doctor, you will pain forever till you die, you know. So we are curing the pain, and the fees of the doctor is very, very small if you are compared it with the pain. If you have a very rich man and you have too much money and you are paining, so okay, if you can live with pain, it's okay, you know. So I can work with you for commercialization and we can convince them.
Thank you, Doctor. I appreciate it.
Okay.
All right. I think that's the end of the question and answer session. Thank you so much once again, Dr. Rami. And thank you, everyone, for joining. And we really, really hope you have learned something from this webinar session. We'll be having our next webinar session in the next quarter. The dates will be communicated in due time. And we just want to use this opportunity to inform you that Accrete Energy will be exhibiting at the upcoming SP NICE conference. We'll be exhibiting at booths 93 to 96, and we hope you visit our booth for more insightful presentations like these, and to get to meet our staff and know more about what we do as a company. Thank you so much, everyone, and enjoy the rest of your day.
Okay. Thank you, Sadura. And I would like to add something. If you need our advice at any time, so Adora and the Accrete team can organize a meeting to help you. If you need any advice, any work program for your next wells, we can help you for that.
Yes, please. Thank you so much, Dr. Rami. Kindly reach out if you would like more business or technical advice or consultancy service. Thank you.
Okay. Thank you, Adora. Thank you.
Bye.
Thank
Bye
you,
bye.
and bye-bye.
Thank you.
All
Bye
right.
bye.
Thank you. Thank you.